here to talk today about IPA, enabling connectivity on the Snapdragon Compute Platform. So I have been working for Linaro for the past 8 or 9 years, something like that. And of those, the last 5 years, I've been working on working with Qualcomm. And for all the time I've been working with Qualcomm, I've been working on the Upstream Linux IPA driver. So prior to Linaro, I was still working with Linux. I was working on clustered storage applications, including Ceph, RBD, and prior to that, I worked at Silicon Graphics on XFS and their clustered XFS product. I've been working with Linux since around 2000, and before that, I did mostly Unix development. So now Qualcomm, so I've been working with Qualcomm. Qualcomm is a core member of Linaro. That's the highest level of membership that Linaro offers, and that just means that they work very, very closely with us. I work in the Developer Services Organization, and we work in close partnership with Qualcomm, and we work to improve the Linux, well, actually not just Linux, but upstream support for their platforms and for those of some of their customers. Qualcomm has quite a few people or companies using their SoCs, so we help them as well. So today I'm going to give a short introduction to the Qualcomm Snapdragon Compute Platform. I'm going to talk a little about the Internet Protocol Accelerator, or IPA, and its role on these systems. I'm going to talk about IPA support in Linux, and then I'm going to dive a little bit closer into the driver itself. And I'm going to talk about initialization because there are some special activities that have to happen during initialization for IPA. I then talk a little bit about power management for IPA, and then the need for the IPA driver to be aware of modem state and events on the modem's lifecycle. And then I'm going to end with some discussion of the current, of recent and some future development. So the Qualcomm Snapdragon Compute Platform. This is a family of systems on a chip, SoCs, aimed at powering Chromebook and Windows laptops. They're capable processors, they are low power, they offer fanless mobile computing, and these also include an embedded 5G or LTE cellular modem. Their words are that this provides virtually anywhere internet connectivity. So these SoCs are used in Snapdragon laptops, and there are several of them out there already, quite a few maybe. I mentioned 2 of them here, the Acer Chromebook Spin 513, which is a Chromebook, it runs Linux. And then the other one that I mentioned is the Lenovo Yoga C630. That's a Windows platform. And there are others, and more coming, I don't know, every month or something. There's quite a few in the pipeline, I think. Anyway, these all support working with cellular data connections right out of the box. But in addition, for example, the Yoga C630, you can run the latest upstream kernel on it with a Debian or Arch Linux distro, and it too will just work even with LTE. So I'm going to mention system on a chip here, mainly because I want to point out the components that I'm mostly going to be talking about today. So a system on a chip, an SoC, is basically a single device, a single silicon device that includes many components that were once separate components on computer systems. So it's got a graphics card, essentially. It's got Wi-Fi and Bluetooth. It's got other I/O, and it's got the main processor, the AP, and also in this case we got a modem. So here I point out the Cryon 494 cores. It's actually multiple chips, but I call it collectively the AP. That is the part that runs Linux on the SoC. And then there is also a Snapdragon X24 modem on this particular one. And that too is basically a complete complex processor. It's not just a dumb device, it runs like a full operating system. So IPA, the role that IPA plays is that it carries data between the modem and the AP. It sits between the two, and so it transports network packets between the modem and AP. In the process, it also offloads some functionality, and it does that. It's designed to do that so that it can reduce the processing load on the AP and on the modem as well. And it also, when you reduce AP processing load with a component such as IPA that uses less overall power, the net result is that there is lower power consumption. So the IPA is capable of fairly independent operation. It works together with the modem and AP, but it also can do some things sort of separate from those two after being programmed to do that. So even though it operates somewhat independently, the AP and modem both share some responsibility for managing the IPA hardware. So here is a very, very simple crayon sketch of what I'm talking about today. We've got the SoC, the overall system on a chip. It has an AP portion, it has a modem portion, and it has IPA, which carries data between the AP and modem. You see some little up and down arrows. Those represent channels, communication channels. For IP, there are a number of channels, and each one carries data in one direction. So two of the AP channels, one coming in and one going out, will be carrying the data to the modem, to and from the modem, in order to represent a single modem device, or rather network device representing the modem. And on the other side, the modem has its own channels for carrying data to the AP. I didn't mention this yet, but this is being pre-recorded, but I will be available online in the chat to try to answer questions during the talk. So if you have any, please feel free to speak up in the chat, and I'll see what I can do. So this is kind of duplicating what I've already said. These SoCs have an AP running Linux and a modem, and IPA carries data between the two. So what I wanted to show here, though, is that what the IPA driver in Linux does is represents the modem's network capability as a network device on Linux, very much like what Ethernet, Eth0, or Wi-Fi might look like. So that's the overarching goal, is to have the IPA driver present a network device representing the modem. Now I show here in parentheses that there's an RMNet Data 0 device as well. And I say this kind of as an aside. I'm not really going to go into it much, but in fact, on the way that the packets are handled by the upstream Linux code, we have RMNet IPA 0, which carries the data directly from the IPA hardware to and from. But then RMNet Data 0 is like another layer provided by a different device driver, the RMNet driver. And what that is that the data carried now, the raw data coming out of the IPA device is in what's called map format, MAP. And map format is just basically each packet has a header, and what it allows is for many packets to be aggregated into a single receive buffer or transmit buffer. So with many packets, each packet within the buffer has a header, an RMNet or a map header, and the RMNet driver is responsible for basically tearing apart the multiple received packets in a receive buffer into individual packets. And the other thing that it can do is, in addition to having multiple packets in a buffer, each packet can actually be associated with a single multiplexed channel. So this map protocol allows multiple logical streams of data to be carried over a single network interface. So that's all I'm going to say about that. I can talk more about it at some other time, but it's not my focus today. So IPA support in Linux. Qualcomm has their own downstream Linux tree. It's all open source, and it's available for you to review and look and build, I guess. It's on Code Linaro now, and I don't have a link right now on how to get at their current, best, latest downstream code, but they do have downstream code. It supports basically all IPA functionality. So that's that. Qualcomm has their own internal code, or not internal, public, but separate code, downstream code. But for Chrome OS has a requirement that the software that manages hardware needs to be present in the upstream Linux kernel. And so the downstream code that Qualcomm maintains separately is not adequate for Chrome OS. So that is where I started getting involved, is that I have been working with Qualcomm to take their downstream code and reshape it and repackage it and make it such that it was acceptable for upstream to be taken into the upstream kernel. And that happened in March of 2020. And since that time, it's undergone ongoing development. Initially, it added some support for other SoCs or other versions of IPA, but it also has added some features and just generally improved overall. So as I mentioned, this driver was derived, or I think I mentioned it, this driver started as the downstream code, but it has evolved considerably. And so really it's quite a bit different from downstream now. And but it only supports a subset of IPA capability. It does not support everything downstream does. So this talk is all about the upstream driver. The upstream driver for IPA is focused on enabling access to the embedded modem. So the embedded modem is the modem that's built into the SoC, like I mentioned at the beginning. This is to distinguish it from an external modem. There could be, for example, there exist now external modems where you can plug in, for example, by USB, or maybe it's a PCIe slot, that you can plug in an external modem into an existing machine and thereby have access to cellular data. So I say this just to say that the embedded modem is for the modem that is present on an SoC, and that's to distinguish it from something that would be otherwise an external modem. Upstream supports only some of the offload capability that IPA offers. It offloads checksum calculations for packets. It aggregates packets, as I said, putting multiple received packets into a single buffer. And it does interrupt coalescing, which is basically delaying when an interrupt would be actually delivered to the AP in order to maybe have multiple, if there were going to be several very rapid succession interrupts occurring, instead of delivering those quickly, we just deliver one and let the AP handle the several that would have occurred once it finally gets a real interrupt. So these are capabilities that IPA that are used in IPA in the upstream kernel. What are not supported is access to PCIe or USB interfaces. And those are things that the downstream code does. And it also takes advantage of some additional IPA capability, which is doing IP filtering, routing, and NAT translation. I say this, and I'll talk a little bit more about this at the very end, but basically this is IPA is able to participate in what I mentioned before about having like an external modem, which is connected by USB or by PCIe. IPA can be involved in that, but at this time, Upstream does not support it. All right, so now that's kind of an introduction to the laptops and to me and to IPA and what it is and what it can do. Now I'm going to talk a little bit about the Upstream driver and the way it's organized and what it does during hardware initialization. So there are several things that are going on during, or that are maybe different about the IPA hardware. And because of that, the initialization that is done for them is done in stages. And so, so here I'll describe them. The first stage I call Init, and what that does is basically does everything that can be done in the driver to initialize it without actually touching the IPA hardware. So that includes allocating operating system resources, maybe looking up interrupts, looking up some other resource information, and configuring that, allocating data structures that are going to be used during regular operation. Anything that can be done before we touch the hardware is done then during the init stage. And that way, you know, if any of that goes wrong, then we don't even bother going any further with initialization. If the operating system can't be prepared for it, there's no point in going on. The second stage is what I call config, and that is that actually touches the IPA hardware for the first time, but it only does so in sort of primitive ways. There's this register-based interface for configuring IPA hardware, and so you can look at or write various values into registers. And we do that as much as we, we do quite a bit of that during this config stage of initialization. But there are sort of, I'll say, larger kinds of initialization, like I'll call it bulk initialization here, which can occur, but it only can occur once we've initialized this other thing called the GSI layer. And I'll describe that in a second. But so setup does everything we can with, config does everything we can without actually having the GSI layer ready and initialized. After that, we enter the setup phase. And the setup phase is where we can do some sort of larger scale initialization and everything else that needs to be done to prepare the hardware for operation. The final step is what's called a handshake. And that is kind of special because this is a coordination stage where the AP and the modem will actually talk to each other in order to make sure that they are synchronized in their shared access to the IPA hardware. The IPA hardware, as I mentioned, is kind of jointly managed by the modem and the AP. And so this is sort of an initial, this handshake is sort of like, all right, let's make sure we're all in agreement on how things are going to work. And then we can proceed and to go into normal operation. So I mentioned GSI. GSI is the generic software interface. It basically is a means to provide bulk data transfer between two entities. The entities in our case will be between the AP and the IPA hardware, or between the modem and the IPA hardware. And so what it basically operates on using ring buffers, rings, shared ring memory areas. So as an example, let's say the AP wishes to transfer data to IPA, which would then be processed and passed to the modem, for example. The AP would allocate a buffer in its host memory. It would set up a transfer descriptor that refers to that buffer in host memory, and it would prepare the buffer so that it's able to be accessed by IPA. And then a special doorbell register would be written, and that basically says, GSI layer, there is a new transfer for you to process. And at that point, the GSI layer would get interrupted, and it would then process, it would look for the new transfer descriptor, and it would perform whatever operation that descriptor described. Once it's complete, the GSI uses a different mechanism, which is another ring, but it just goes in the other direction. It would generate what's called an event. It's like a record to say, you know, something happened and here the following is what it was. And so the event would then be generated by the GSI layer, I'm sorry, by the IPA layer, pass it through GSI, and that would get it. That would then trigger the AP to be interrupted to let it know that a previous transfer it had initiated had completed. Anyway, this is kind of this is not an unusual sort of a mechanism for data transfer between hardware layers, and this is what GSI is. It's a separate layer that, that is used to transfer data. The reason it's important to point this out is not just that it does this cool bulk transfer in a nicely isolated way. It is that it's a separate thing. It must be initialized separate from IPA. And until it's initialized, the IPA driver can't proceed with its, it can't complete its initialization. So the GSI initialization has kind of like 3 steps. It's basically load the firmware, which is just writing kind of a file into memory in a certain location, update a few registers to maybe say this is where the firmware executable begins and maybe some other configuration parameters, and then just say go. And once that happens, then GSI is available, it runs, it just runs indefinitely, and then at that point, the AP can proceed with the initialization, with the setup phase. So, yeah, I'm just gonna go back real quick. Yeah, so we've got init is operating system resources. Config is things that don't actually require GSI, and then setup can happen after GSI is available. So this GSI initialization can actually be done in 2 ways. One way is for the AP to do it. So the AP would load the firmware and push it and do the registers and say go, and then the AP knows it has initialized GSI, and then it can proceed with its setup phase. On Chrome OS, it's done a little bit differently. Instead, on Chrome OS, the modem initializes GSI. And the issue there is that in that case, the AP needs to know when the when the modem has completed the GSI initialization. So what happens is that there's a special interrupt, and the modem, once it has finished its GSI initialization, it sends the interrupt to the AP, and the AP then knows that GSI is initialized and it can proceed with setup. So on Chrome OS and in that kind of a modem init environment, the AP completes its config phase, but then must wait to complete its setup until it gets this notification. So the last step, I'll go back really quick. The last step is the modem handshake. So at this point, once setup has completed, basically everything's ready to go. And now it's time to do the modem handshake. So I said before, AP and modem can communicate, they both share access to the IPA. They have a thing called QMI, Qualcomm Messaging Interface is what I think it stands for. QMI is kind of an out-of-band signaling mechanism. It's more than just signals, it's actually a communication mechanism. And there are different QMI protocols that can be used for various control activities. So one of those protocols is one that's used during IPA initialization. And so the way it works is basically when either the modem or the AP is ready to participate in QMI communication, it kind of sets up an endpoint for communication. And that act actually triggers something on the other side to notify, hey, your partner over here, your peer is ready for communication using QMI. So they basically each advertise that they're available to talk with QMI using their QMI channel. When that happens, when the AP discovers that the modem is ready, it initiates the handshake. And I'll go into the details in the next slide, but basically this coordination is important because the modem avoids really touching the IPA hardware until the handshake is complete, because only when the handshake is complete do they know that their access, that everything's ready to go, and that the AP has done its part to initialize things. So here's the handshake protocol. Each is basically a message, but it's kind of an RPC. So each one, almost all of them will basically have a response that indicates the message was delivered reliably. So the AP starts, or the first thing that happens is the modem sets up its ability to handle QMI messages. And that's basically a message to the AP to say, I'm ready to start our handshake operation. The AP then really starts the protocol, the negotiation. It builds a structure full of sort of the operating parameters for both the AP and the modem to use that are related to IPA. There are some buffer sizes, there are various parameters, and they just have to agree on what they're going to use. So the APA builds up a structure filled with these parameters and sends them to the modem and says, okay, here's what we're going to do. Here's what we're going to use together. And please initialize using these parameters. The modem then sends back two messages in one or the other order. One of the messages is, or one of the requests is, that the modem can say, when you have received my ready message, please let me know. And that would be, and I'll go on and this maybe make it clear. The second thing that is sent in one or the other order is that the initialization step that was requested by the first AP message, the modem sends a message saying, I'm done. I've finished my initialization, so I'm ready. So if the third message in this list here occurred and says, you know, the modem wants to know when the AP knows it's ready. If that happens, then the AP will send a final message to the modem saying, I got it, I know you're ready, we're all ready to go. So that's the handshake. Once this is complete, both sides know that they can proceed with normal operation of IPA. So the handshake is the first step to coordinate AP and modem access to the IPA hardware. It's done every time the modem boots. So it's possible for the modem to shut down or crash and then get rebooted. I'll talk a little bit about that later. And so if that happens, if the modem comes back up again and reboots, then this handshake or some form of it occurs again to make sure that everybody's coordinated before they begin accessing. So the AP is the leader, and it initiates the process. But once the handshake completes, both sides are able to access IPA independently. But there's one more big piece that is missing so far, and that is IPA Power Management. I'll talk about that next. So the IPA and the modem and the APs, these SoCs are used on power constrained devices. They're used on laptops. That's what I'm talking about today. But there are other chips from Qualcomm that are used on mobile phones, lots of mobile phones, and IPA is used on in those environments too. So they're very power constrained, which means, and basically long battery life is among the most important things that these things can offer. And so long battery life comes when you minimize power consumption. And the way that works is that you slow down or you stop clocks. The slower the clock, the lower the power, the faster the clock, the higher the power. So if we can slow down clocks or shut them off completely, then we save power. And as a result, it's a good idea to shut down things and slow clocks as much as you can, if you can, in order to save power while operating. So the modem can be put into a low power state. So if you put your phone or your laptop in airplane mode, for example, the modem can be shut completely down and not consume battery power. Similarly, Linux can also suspend itself. It can suspend all the various devices, and it can also suspend its entire, the AP as well, all down to a deep sleep state to save power. That happens, for example, when you shut your laptop lid and everything kind of, the light dims, but then everything kind of goes down to almost nothing until you open things up again, and then it'll restart. It'll bring it out of suspend mode. So the IPA is this separate device, though, and both the AP and the modem need to access the IPA, and they access them independently. If the modem is suspended, or no, let's see, if the AP, let's say you suspended things, and then you open up the lid of your laptop and it resumes. In that case, we need to bring power back to the to IPA, because the AP may need to send packets over IPA to the modem. Similarly, the modem may have sort of stopped operating for a while, but once it gets a packet that needs to be delivered to the AP, it'll need the IPA hardware powered as well in order to carry the data. So the question is, can we suspend the IPA hardware itself when things are idle? And the answer is yes, and we do it using a thing called the Resource Power Manager. And I'm just going to talk briefly about that, but I think it's what allows the IPA to be suspended in this kind of situation. So the Resource Power Manager is a SoC component on Qualcomm SoCs that manage clocking and power for things such as IPA that required shared control. So the way it works is that rather than, for example, the AP having a directly attached device which it can just power off when it knows it's not in use, instead the AP just sort of notifies the RPM that it is no longer using this shared resource. And similarly, the modem can tell the RPM that it is not using or is using IPA or some other shared resource. So what happens is the AP and the modem in this case will vote for what they need. They will vote and say, I need the clock to be running about this fast on the IPA because I'm about to use it for something. And the modem does the same. And the RPM aggregates these values, and then based on what it sees, will set the clock rates on IPA in this case, based on what those votes were. And if there are no votes, then the RPM can then shut down IPA hardware, suspend it, turn off the clock, and save all power for IPA. So that just makes the AP and modem responsible for voting for IPA power or clocks whenever they know they need to access it. So that's it. I mean, that's how that works. The Resource Power Manager allows us to be able to shut down this shared IPA resource. So now we have a different topic, another switching gears. I mentioned before that I mentioned before that the IPA is used by both the modem and the AP, and I also mentioned that the modem is able to could crash conceivably. Hopefully that doesn't happen much, but it could, and if that happens, we want the AP to be able to tolerate it and even recover from it. So I also mentioned at the very beginning that the modem is not just like a dumb device. It's a complex processor. It runs a full real-time operating system. It supplies lots of functions and lots of services. But it is actually operated it's managed by the Linux Remote Proc framework. And Remote Proc framework it provides a general way for Linux to say there is a separate device that is fully under the control of Linux, and it is able to load firmware on that separate device, boot the separate device, monitor that device once it's operating, and if it stops operating, notice that and take take action when that occurs, including for perhaps picking up crash dumps. So so remote proc is the Linux framework that sort of manages the modem. And one of the features that remote proc offers is that a driver like the IPA driver can register to receive notifications on events in the state change of the separate device, in this case, the modem. So whenever the modem boots, whenever it shuts down or crashes, remote proc handles that, and it also notifies IPA that these events have occurred or maybe are about to occur. And I'll mention that. I'll talk a little more in a second. So yeah, there are 4 notifications. The first is about to boot. So right before the modem, I think it may be before, I don't know if it's before or after firmware is loaded for the remote processor for the modem. But in any case, before it actually boots the modem, it will send out a notification to those that have registered, in this case, the IPA driver, to say we're about to boot the modem. And that gives the IPA driver a chance to do some initialization or respond to that event. I don't remember if this happens right now, but it's possible, for example, that the IPA driver might learn the modem's about to boot. Let's initialize some various state variables for what we record as the modem state. It's about to boot. Maybe we've got a statistic counter and we zero the statistic counter for this episode of the modem booting. Anyway, when you get this, when the modem's about to boot, remote proc will notify those that have registered to get those notifications. The next one is that after the modem has completed its boot, another notification is sent, and IPA in that case, actually the IPA driver, when it receives that notification, that triggers kind of a setup that says, okay, the modem's up, so we should be expecting to receive this or to get this handshake operation started. So that's the notification we use there. The next 2 are shutdown related. The third event is the modem is about to shut down. Actually, let me go the other way. The next one is the modem has crashed. So while it's monitoring the modem, it may discover that the modem has gone away or is no longer responsive or something. And at that point, it determines that the modem has crashed. And the remote proc system will take some action when that happens. But before it takes that action, it notifies everybody that wanted to get notified. And in this case, the IPA driver will be notified, hey, the modem has crashed. And in that case, the IPA driver takes probably the most action. And what it needs to do is it's possible at the time of a modem crash that there's some sort of in-flight activity where the modem may have sent some data into IPA and it never got completed, never got received, or it's backed up and it's queued for delivery or whatever. So there might be some in-flight, packets. There may be some other intermediate state. And basically, if the modem crashed, that state needs to be reset to a well-defined an initial state so that we can restart everything and bring things back again. So a crash notification, in response to a crash notification, the IPA driver will clean up all the in-flight modem activity in the IPA hardware. It'll basically reset the IPA hardware to an initial state, very much like what happened before the very first time the modem booted. And then the final notification is that crash handling is complete, and it's just saying we're done with that. And the other thing I'll mention now is that shutdown is basically, at least from the IPA driver's handbook perspective, shutdown is just a clean crash. We don't care if it was a clean shutdown or a sudden abrupt shutdown. We just go and clean up initial state and reset everything so that it's in ready for the next boot, the next modem boot. And here too, shutdown, if it's a clean shutdown, the 4th notification is basically saying, okay, we have completed the clean shutdown. And then once we've got to that point, then we can restart the modem again. And the remote proc system does that. There's an option that you can tell it to automatically reboot if that occurs, but it's an option. So, all right, so that's kind of the end of my main coverage of the IPA driver and the IPA overall. I'm now going to talk just a little bit more about recent development and about kind of what's the next development that's going to happen in the IPA driver. That's our plan. So first of all, since it first landed upstream 2 years ago, we have added support for several new different versions of IPA hardware, newer ones. Some people are actually, not I, but some people are actually working on supporting older devices and have had some success with that using the upstream kernel. Last year, the biggest kind of feature added was that runtime power management was added. So runtime power management is basically an automated way to save power as much as possible. A driver that registers for runtime power management provides some callback functions that say, you know, when you need to suspend me, here's the function you call, and I will make sure we get suspended. And the other one is the inverse, is to resume things when it's time to bring things back to life again. So what runtime power management does is it has those two callbacks from a driver. When a driver registers, it says, I would like to be suspended if I ever have X amount of inactivity. And in the case of IPA, we do that with a half a second, 500 milliseconds of inactivity. If the IPA hardware has not been used in a half a second, the power management system will automatically say, okay, let's suspend it, shut it down. And then once it's suspended, we just have mechanisms such as an interrupt from the hardware to say, hey, there's some new activity, you need to wake up. So, runtime power management was added to the IPA driver, which means that it basically starts operating as much as it needs to, and then as soon as it's idle for a half a second, it suspends it again, saving power. And then when it's needed again, the driver automatically brings things back to life again, and the cycle repeats. So that was added last year. Very recently, I have added, or I have implemented what I'm calling monitor support. In the downstream code, they call it something else. They call it ODL and ADPL. And so what monitor support does is exposes some of the internal packet processing that's going on in IPA. So as I mentioned, you know, we know that it carries, the IPA hardware will carry packets between the modem and the AP. But in some other configurations, in the configurations supported by downstream, there are other entities that can exchange packets as well. So it might go to the PCI bus, between the PCI bus and the modem, for example. And so there can be a great deal of packet activity from multiple endpoints or multiple entities communicating. But regardless, what the monitor feature does is actually expose some information about every one of those packets. It actually duplicates every one of those packets, or at least up to a certain relatively small fixed size. So every header and multiple layers of headers plus a little bit of data from each packet will get replicated and exposed through this monitor feature. So that's basically complete. There's a few details we're working out. This will be going out for review for upstream soon. I'm not exactly sure when, but maybe within a month or something like that. So that's sort of the most recent development. The future development is more like what is supported in the downstream code. So I mentioned before the possibility of having a modem device that might be on a USB stick. and that kind of a cellular modem could add functionality to add cellular data functionality to just a regular x86 host, for example. So in fact, the way that kind of a device is set up is that is like this. It's very much like what I've talked about with the embedded modem for a laptop. It has its own AP. In this case, it's not going to be as powerful as what an AP in a laptop would have, but nevertheless, it has its own AP. It runs Linux, and so that AP is responsible for configuring things and detecting that the PCIe endpoint is active or that the USB got plugged in somewhere. So what's different or what's special maybe is that you can see my little two arrows going to the PCIe endpoint that go directly to IPA. So IPA is the capability to transfer data directly to PCIe and efficiently. And that way you get to basically not have to touch this little AP processor in this chip. So the AP in the chip can detect that the PCI endpoint is active. It can do some configuration of IPA. And once it has performed that configuration, it can allow the IPA, it can allow everything to just operate. And from that point forward, transfers between the host on the left in this picture over the PCI bus and into this SoC that's got the modem on it. Those transfers occur unhindered by the AP. They just go directly over IPA and they get transferred efficiently and without any load on the main processor, on the main AP in this case. So that is our goal, is that the downstream, the upstream Linux code can handle the left side of this diagram, which is that the host can talk with a modem of this type. It can handle sort of the right side of this diagram, which is to say we've got the embedded modem is accessible by IPA, but we don't have the part that allows, in the upstream Linux kernel, we don't have the part that allows the PCI endpoint to access the IPA directly. And so I'm going to talk a little bit more about that. So the PCIe endpoint, there's a thing called MHI, modem host interface. And it's kind of a software abstraction of a networking capability that goes over PCIe. It can actually go over other protocols, but in our case, it's going to be PCIe that runs MHI protocol or MHI interface. That is already in part supported. As I mentioned, the host side has the ability to use MHI to talk with a modem. But what we're working on now, Mani from Linaro is working on getting the MHI endpoint support to support the PCIe endpoint side of that connection, operating with MHI software. So that's required for this to work. The next thing that's required is what's called hardware accelerated MHI channels, and that's basically IPA. It means that we're using the IPA direct hardware channels to carry data, not other non-accelerated mechanisms for transferring data over MHI. And then the third thing that's required for this will be some user space management utilities. That's not my area of expertise, but it's going to be required. It's going to be basically needed in order to determine, to configure networking and some routing and things like that. Beyond that, so first of all, initially our plan is to do all of that PCI-based attached modem. We're doing that, let me go back to the picture, such that when traffic comes over the PCI endpoint, it will go to the AP, and then the AP will use its existing ability to pass data to the modem, to the embedded modem. So that is not leveraging the IPA accelerated hardware, the accelerated path that avoids using the AP. So that's our initial goal, though, is that we'll do it that way because it basically is a stepwise a step toward what we ultimately want to do. To do the ultimate thing, we need some additional functionality from the IPA hardware, and that includes doing some filtering, IP filtering, so that we can detect when a new connection is established, for example, or various events. We can detect those things, and the filtering capability allows us to do that. Basically, if a filter rule matches, then the AP gets notified, and then the AP can take some action in response to that notification. Another feature is routing. It may not matter so much with AP and modem alone, but for when we have additional things like the PCI endpoint, or there could be USB in here as well, there are other endpoints that packets can be routed to. And so IPA has the ability to have some routing rules and take care of hardware routing of packets without intervention by the AP, at least once they're configured. Here too, it would be that essentially you would get some kind of a special notification that says, hey, a route needs to be created, and then the AP can then program the IPA hardware to handle that for the future, and then say, all right, go ahead and proceed. So, anyway, this is beyond the sort of just using the PCI endpoint. What we really want to do is get to the point where we get filtering, routing, and the other thing that IPA can do is NAT calculation. It can do some transformations of packets as they pass through, so that they can do network address translation and basically rewrite certain addresses and things, and then update checksums so that they look as though they were originally sent the way with the modified address. So in order to do those things in hardware, there's going to be a lot of work getting those things into the upstream kernel. And I say it's a lot of work. It's intrusive in several layers into the network stack. Doing it sort of the right way and getting input on what the right way to do it is going to take some time, but we want to get it right, and that's our objective. This is kind. I mean, I would love to be working on this later this year, but at this point, I think it's more of it's a goal. It's what we'd like to get to as soon as we can, but it's gonna be tricky getting there. So that's basically the end. I'm going to summarize. Snapdragon Compute Platforms are Qualcomm SoCs that were designed to be used in laptops like Chromebook and Windows. These laptops are available now. You can run Chromebook, or you can run Chrome OS, and you can run Windows on them. You know, it's like any other Intel device. It works just like you would expect. But in addition, these things incorporate an embedded 5G or LTE modem, and they incorporate this IPA device in order to carry the cellular data traffic and reduce the power consumption and offload some of the load on the modem and the AP. I really haven't talked about Windows. Windows is not my focus. And so Chrome OS uses the Upstream Linux kernel and the Upstream Linux IPA driver, and that supports access to the embedded modem. I talked about how the AP IPA driver performs staged initialization, including coordinating with the modem to access the IPA hardware. I talked about how the AP and modem each is responsible for requesting power for the IPA hardware when they're about to access it, and that the resource power manager is present because it's present, it's possible to actually suspend the IPA hardware completely when it's in use by neither the modem or the AP. The modem itself, the whole modem, is started, stopped, loaded by the Linux remote proc framework, and IPA driver registers to receive notifications on modem events in response to them. Work is now underway to enable upstream Linux support for PCIe-based modems, and then later on USB modems probably. And someday we'd like to have the IPA NAT filtering and routing capabilities be supported in the upstream kernel. That's not today, but the discussion has started, and we're trying to work toward getting that done. I'm going to close with a few resources here. The first three, well, the first one is just a kind of a Linaro page for what we do in developer services in support of Qualcomm platforms, including those of not just Qualcomm, but Qualcomm's customers. The next link is Qualcomm's sales page, marketing page for their mobile compute platform. And there's plenty of information there about the laptops that are available and that kind of thing. I didn't really go into this, but there's an ARch64 laptops project on GitHub, and their goal there is basically to do support for ARM64 laptops, and that includes IPA. So that is a link to the GitHub page for that project. The next three are three presentations that were made that are related to this, either MHI or IPA. And they were done at the last Linaro Connect, which was done virtually. I think it was in February or something like that. And then finally, there are two blog posts by Mani, who I mentioned before, and also Loic. Both of these guys are from Linaro, very smart guys, and they've done some, these are some blog posts they did about some of their work that's related to this. And that's it. With that, I guess I'm going to close. Again, I should be online in the chat right now, answering any questions that have come up. And I hope this has been useful, and I appreciate your attending this session. Thank you. Hi there. If anybody has any questions, I think Christine has allowed people to unmute if they'd like to ask anything of me. And if there's nothing, we can just be done.
Yep, they just have to raise their hand, then we can unmute them.
Oh, okay. Well, then please raise your hand. Well, very shy. I don't have the link available right now, but there was just earlier this week, there was a new Windows announcement of, I think it was Lenovo. Anyway, maybe Nico or somebody else has a link to that and can make it available, but it seemed like a pretty nice, capable machine. Let's see. It's IPA QCOM specific, meaning what if someone has M-core, not modem? So IPA is Qualcomm specific. It is Qualcomm's technology for handling, for offloading these things. So yes. All right. Caleb says, thanks for all the work. It's been amazing to be able to have working mobile data on mainline Linux on Android devices. And that's actually great to know. I haven't actually worked directly with Android. I have been working almost exclusive in the Chrome OS environment. And, one should think that it should just work in other environments, but that's not always the case. So it's great to see, Caleb, that you are saying that it's Android devices running at Linux user space. So anyway, clearly this stuff works well enough to be used in different environments than just Chrome OS. We'll say that. is it interrupt driven? And follow-up question, is the memory shared between AP and modem? Yes, it's interrupt driven. I mentioned that there is interrupt, I think I called interrupt coalescing. I think that's a common term, but there is, it's interrupt driven whenever there is hardware, or whenever there's packets available to receive, or whenever a send of a packet has completed, the AP can get interrupted in order to find out whether, or to continue processing. The hardware, the IPA hardware, can manage some of the interrupts a little bit to make it so that the interrupts are not as demanding on the AP. The other thing is that the IPA driver is every channel operates using NAPI, the new API, which is 20 years old or something like that. And what NAPI is an extension to interrupt handling. And it uses polling. So basically what NAPI does is when an interrupt occurs, we disable all interrupts of that type. And then once what the interrupt handler does once it begins processing is to look at all interrupts, including new ones that have happened since the first interrupt arrived. This just, it's able to know that a new condition has occurred even though it's no longer getting interrupted. So because we use NAPI, you can handle very much activity all at once without having the overhead of switching, of doing context switches in order to do lots of interrupt handling. I'll leave it at that. So yes, it's interrupt driven. Let me go back to a few more questions. Right. Oh, is the memory shared between the AP and modem? So yes, there's actually at least two kinds of memory. There is AP memory. There's actually a little bit of memory on the IPA itself, but that's mostly used for sort of like very hot access to memory. So I mentioned that that the IPA hardware has the ability to routing and filtering. Those special table rules and things will be stored in memory that's actually IPA resident. But as far as the data transfers and things are concerned, the AP and modem each have their own private memory. So when a transfer occurs, the AP will allocate, okay, the ring buffers, the rings themselves are located in AP memory or in modem memory for the modem transfers. And then the rings themselves will then point to buffers that are also resident in AP memory or modem memory. And so IPA will then access the shared memory. Then it's able to access the AP's memory or the modem memory in order to achieve its transfers. Do you know, can you share any details about getting the runtime logs from the modem processor? I do not know. I think that is related to I mentioned the monitor capability that is exposing what's happening inside the IPA, which I think uses on-device logging. It's possible that that is related to getting logs from the modem, but I don't really have very much visibility into what's going on in the modem myself. And so I kind of expect, I'm not aware of getting access to those things or how to get access. And I would say my gut reaction is no. I don't know how to do that. Okay, thanks for the information. In case of PCI, if IPA is stuck or died, the x86 will be able to reboot IPA and modem. Probably. I haven't gotten very far on that. Yes, I think that's the way MHI works. I think MHI has the ability to reset a channel, and so I think, yes, I think if the x86 or whatever host, it could be an ARM host as well. If the host determines that the PCI is stuck or hung, then I think it can issue a reset and the channel will get reset and then everything go back to normal. I haven't implemented those details yet, so I don't have a lot more to say than that, but that's generally, I think, how it's going to work. Are there any other questions? All right, well, seeing none, I mean, I'm done. We'll maybe give it another minute, and if people want to chime in, that's fine. Otherwise, I think we may be done. Thank you again, everyone, for joining, and I appreciate the questions. All right, let's call it.